Okay, hi guys. Welcome to Tuesday's lecture. I hope you had a good weekend. Some very quick administrative announcements. So we are sitting here on July 21st. So your assignments are being marked as, I guess, some of them might already be marked. Some of them may be marked in a few days. The solutions are posted. Please have a look. As always, if you are feeling like you're looking at the solutions and they still don't make sense, by all means, please reach out to your TAs. That's why they're there. It could either be a question via an email for clarification. It could be you asking to have, 10 minutes, 5 minutes, 15 minutes, whatever amount of time, one-on-one sessions on Zoom or Blackboard Collaborate. And if for whatever reason your TA is busy or whatever reason, if you need to reach out to me, you can always reach out to me as well. But I would like for the first line of support to be your TAs. That's pretty much why the TAs are there, is to really help the students first. You have a lab that is due Wednesday evening. So that's just a reminder for you there as well. That's the first lab. And I think lab 2 will become available Wednesday morning. So, there's some overlap there as well. You have a tutorial. Every single one of you has a tutorial the day before the midterm. So hopefully you find that helpful as a bit of a review. And then, of course, the midterm is on Friday morning at 8 a.m. Eastern Standard Time. As per my announcement on the weekend, I was saying, for those of you who are west of the GTA, that would mean you would have to wake up substantially before 8 a.m., which I think is just too early. Now, we're lucky with the midterms that they're not regulated by the university. They're not regulated by the Office of the Registrar. So, I have the flexibility very easily. I have the flexibility to accommodate the people who are west of the GTA. So if you haven't filled out that time zone survey yet, please do so. I think later today, I'm going to sit down and pull the results from the time zone survey. Maybe tomorrow, because there's going to be some of you guys viewing on YouTube later. So I might just do it tomorrow and give you guys a bit of a time to answer it if you haven't already. And then if you're west of the GTA, I'm going to adjust your start time so you start at 8 a.m. In your own local time. So that's why I need to know what time zone you're in. Okay, and the last piece of announcement administratively I want to show you, there is a colleague of yours, a fellow student, who, let me find it here, there we go, who has very, very graciously offered to type up lecture notes and given me permission to post them on Canvas for you. So I've posted the first one that they produced, which is the electricity one, because it's really the first topic that I didn't make my own typed notes. So I've posted them for you here. So her name is on them here. So Andrea, thank you. That is a very gracious thing that you've offered to do. It's a huge amount of effort and time, as I'm sure Andrea knows, to type up notes. And I can't thank you enough for that. So I would like to give you a shout out as a thank you for that. So those are going to be there whenever she has them ready. Again, there's no pressure on Andrea. I don't want to make her feel like she's obliged to do this. So however long she can keep this up, if it's just this is the only one, or if it's until the end of the course, whatever, it's whatever amount that she does I am very appreciative of that, and I hope everyone else can be appreciative of her efforts as well. Okay, I think that's everything in terms of administration. So I'm going to jump to this, and we are going to sort of resume where we left off. So I hope everyone had a chance to, I know you were busy doing your lab. I had some good lab questions over the weekend. Gideon had office hours for lab-related questions yesterday. I hope you were able to take advantage of that if you had questions as well. I hope, in addition to all of the lab work you've done, I hope you've found some time to sit down and sort of review some of these lecture concepts we talked about on Thursday. Not only is it good to sort of keep up with the lecture because it's fast moving, we do have a midterm on Friday, and studying for the lecture material would have inherently been also studying for the midterm. So if we have any questions, maybe halfway through or something, I can take them. But for now, I want to finish the electrodynamics unit. So we finished off on Thursday with current, and specifically we were talking about Kirchhoff's rules. We talked about loop rule and junction rule, and we finished off with, oh, of course, there we go. We finished off with a fun little brain teaser, if you can even call it a brain teaser, using loop rule with this fun little circuit here. And the last topic in electrodynamics that we have to talk about is something called RC circuits. And I've given you a bit of a tidbit. Now, actually, Google's how to spell defibrillator. So there it is there. And I said, for those of you who are in life science aiming for med school, I tried to find an example that would be useful for you. I know there are some other people in the class, perhaps in forensic science, and it's likely you'll never have to use a defibrillator in your life, but it's an interesting idea nonetheless. But an RC circuit, one application of an RC circuit is a defibrillator. So what is an RC circuit? Why do we call it an RC circuit? Well, quite simply, R just literally means resistor, and C means capacitor. So an RC circuit is literally a circuit that has a load, like a resistor, and a capacitor. As we see here, it's called an RC circuit because there is a resistor and a capacitor in it. Plain and simple. I said it before and I'll say it again. Physicists do not like words. We will try to name things as logically and simply as we possibly can, because we don't have the ability to name things in an obscure way that we then have to remember what an arbitrary phrase means, right? So RC circuit because it's got a resistor and a capacitor. So what's the significance of an RC circuit? Why do we even talk about it as a thing? Well, let's look here. If we were to take this circuit, I'm going to change my color to blue for a second. Actually, I'm going to change it to red, because current is, conventional current is a flow of positive charges, and positive charges are always red in textbooks. So I'm going to change my color to red. If you take the circuit here, let's pretend the switch is closed. I mean, if it's open, obviously nothing happens. So let's say we close the switch. So we now get, well, actually with gray, I'm going to complete the circuit in gray there. So let's say we close the circuit, and what's going to happen is this is going to have a potential difference. Let's say 10 volts, whatever the battery is. It could be a AA battery, it could be a 9-volt battery, who knows? Let's just say it's a 10-volt battery. And what that's going to do is that's going to create a positive 10 voltage on this side of the battery, and that's going to create, well, 0 volts on the other side of the battery. So it's a 10-volt difference, obviously. And that potential difference, as we've learned before, is going to cause charge to flow, right? If you have a non-zero delta V, you're going to get a flow of charges. So this potential difference is going to result in, one positive charge kind of flowing on this side, and then there's obviously going to be one negative charge that flows. Now, the voltage across a capacitor is a function of how much charge is there. Now, at first, when you first close the switch, some charge will flow, but it won't immediately charge all at once, right? Like something has to get there first. So what happens is some amount of charge gets there first, and when some amount of charge gets there, the voltage across those plates goes down a little bit because it's becoming fully charged, right? There's inherently a maximum amount of charge that can fit on a plate. So, the quota is a little bit filled up when one charge gets there, but it obviously can hold more charge. So then the second charge comes in, and then when the second charge is there, there's a second negative charge. So it's building up charge slowly. Well, I shouldn't say slowly. In real life, it happens pretty quick, but point being, this doesn't happen all at once. And then when the second charge arrives, it's becoming more and more full, just like when you're filling a bucket. When you turn on the tap and you're trying to fill a bucket, it's not like the entire bucket fills with water all at once, right? It fills up slowly. And this keeps happening. Charge will keep flowing out of the battery until you have, so let me write this maybe over here. Charge will continue to flow out of the battery until the capacitor is fully charged. And at that time, once the capacitor is fully charged, then there is no current. There is no current coming out of the battery because the charge has nowhere to go. You know, it's like when you turn the hose on outside from the house, the water is on, but unless you squeeze the nozzle, there's water in the hose just ready to come out, but unless you squeeze the hose nozzle, no water comes out, right? It's because the capacitor is fully charged, there's nowhere for the charge to go, so no more charge comes out of the battery. So let me change color here because it's a different thought. Once the capacitor is fully charged, you can remove the battery. And if you remove the battery, because once the capacitor is fully charged, the battery isn't doing anything. There's no charge flowing out of the battery. There's no current flowing out of the battery. The battery is useless. So once the capacitor is fully charged, you could actually get rid of the battery and just, replace it with just a solid wire connection. And then for a very brief moment in time, the capacitor is able to act like a battery. It's got all this charge built up in it. And if able, like if you close the circuit, the capacitor can release that energy, release that charge, and power the resistor. It can power the light bulb. It can send an electrical current through your heart, as a defibrillator would do. So that's what an RC circuit is. Now, the whole premise of what I was trying to say here is that it doesn't happen instantaneously. The charging of a capacitor is a non-zero amount of time. And the discharging of a capacitor is also a non-zero amount of time. Things don't happen instantaneously. So here are the brief summary points of what I just said. So when the switch closes, charge will start to flow. Now, I want to clarify something. Charge will start to flow, I'll say, out of the battery. If charge flows, this is the definition of a current. So there will be a current coming out of the battery as it is charging, as the capacitor is charging. Now, this is where I want to have a point of clarification. Although there's a current out of the battery, what is the current through the capacitor? And think about this very carefully, okay? Let's recall what a capacitor is. Right? A capacitor is two parallel plates. They could be rectangular, they could be circular, they could be two triangular plates held close together. The shape of the plate is irrelevant. The fact that they're just two parallel plates is the important part. However, there is an air gap. There is an air gap there. So charge is building up on each plate, but is there a current through the capacitor? Is there a complete circuit that the capacitor creates? The answer is no. Now, of course, we learned about lightning and how with enough voltage you can push electricity through any material, including air. So you might be thinking to yourself, okay, well, with enough voltage, there will be a complete circuit, and you're right. This is why when you look at a capacitor, And this is where I really wish we could be in person right now, because I could bring in a capacitor from the physics labs, and I could show you with the document camera the writing on a capacitor, but I'm not able to get into UTM. I cannot show you the writing on a capacitor. But on a capacitor, it's rated for a certain voltage. And the reason for that is because if you go much beyond that voltage, you're going to put a spark right through the capacitor. And that would complete the circuit, and that would ruin all the physics of the circuit. You know, whoever designs a circuit, whoever says, well, we need this capacitor, we need that capacitor, it's specifically designed because, you know, there are certain aspects of the circuit that shouldn't allow charge to flow, that shouldn't allow a current to flow. Capacitors being one of them. So if a capacitor all of a sudden allows current to flow, it can ruin other parts of the circuit. So it's very important that, at least in this lecture or in this class, we make that distinction between current coming out of the battery while the capacitor is charging versus current going through the capacitor. Under normal operation, there is no current ever that flows through a capacitor, just charges that build up on a capacitor. Okay, here's the thing though. As charge builds up, the rate at which they build up slows down over time. So at first, when there's nothing in the capacitor, charges are very readily added to the plates. But as more and more charges build up, it's harder and harder to put additional charges on the plates. So at first, it starts charging really fast. At first, there's a large current coming out of the battery. And then as it starts to charge, the amount of current coming out of the battery diminishes. They say exponentially, but it's not quite exponentially. It's, you know, actually, no, the charge is exponential. Sorry, the current is exponential. We'll look at this later with time, but the current starts off at a maximum, and then it slowly decays to zero over time. Now, if we look at the voltage of the capacitor over time, the voltage starts off at zero and slowly, this is what I meant by it's sort of exponential, slowly asymptotically builds up to a plateau, a maximum voltage. And there is an exponential in this equation. We'll look at it shortly. But it's overall, it's a shifted version, a transformed version of an exponential. It's flipped upside down and moved up. You know, if you want to think of grade 11 transformations. Oh, right here. Okay. So this is I guess should have just went to the next slide because it's got it. So this is what's going on physically. Okay. So at first, when you close the switch, you know, when you close the switch right away, there is no charge on the capacitor. So the battery, you know, is free to unimpeded very quickly put charge on the capacitor plates. So the current starts off, oh, let me choose a different color. The current starts off at a maximum. But as charge builds up, then the current gets a little slower or smaller. And then, you know, as charge gets even bigger, the current gets even smaller. And then eventually, when the capacitor is full, the current is effectively zero. So that's a negative exponential. It will decay exponentially with time. Now, this is a differential equation. If you were taking Physics 147, the calculus-based physics, I think they have something similar over on the St. George campus. I think it's Physics 152, which is equivalent to our Physics 147. You know, that physics course is designed for physics majors who are going into physics. You know, there we would actually set up the differential equation for you, and we would solve it using complicated math that is apparently no longer taught in first-year calculus, which is unfortunate, making our meaning the physics instructor's job more difficult. We would go through that, but in this class, I don't want to focus on that level of math, and not only that, even as a doctor or, you know, if you're in forensic science, I can't fathom a reason why someone in life science or in forensic science would need to know this equation, let alone the derivation of this equation. So for the sake of the curriculum, I'm showing you the equation so you have it. We're not going to derive it. And, you know, I think I told you on Thursday, RC circuits are not a huge part of even this class. So I'll give you the equation. Please don't dwell on kind of where it comes from. As long as you can kind of understand it, it's a decaying exponential. Not even exponential, it just decays with time, where it starts off large and eventually will go to zero, because when the capacitor is fully charged, the battery has nothing to do. The voltage is sort of reverse. At first, the voltage across the plates is zero, and then as charge builds up, the voltage on the capacitor gets VC. This is V capacitor, V cap, or VC. And then when the capacitor is fully charged, the voltage across the capacitor is equal to the voltage of the battery. So I'll say when does not start with an A. When the capacitor is fully charged, the voltage equals that of the battery, or the source. The source may not be a battery. The source might be like the wall outlet or something like that. Okay, so those are the two equations. You can even see the truth of this statement in the math, right? As time goes to infinity, you know, meaning it's fully charged, then e to the minus infinity, like if t goes to infinity, then e to the minus, oh, you can't see the blue very well. E to the minus infinity is going to equal 0. That's just math. And then you're going to get 1 minus 0, which is 1. So you're going to get the voltage of the capacitor equals voltage of the source times 1, which is simply voltage of the source. So mathematically, even you can see from looking at the equation what happens conceptually. You know, over time, the voltage will equate to the voltage of the source, which makes sense. I mean, you obviously can't have an end voltage larger than the source. That doesn't make any sense. It may be perhaps conceivable that you have a voltage less than the source, but, you know, no. Everything's a perfect conductor. The charge can build up on the plates readily because it's a perfect conductor. So it will exactly equal the source. Okay, the last equation we need to look at is the charge on the capacitor. And the charge on the capacitor is analogous to the voltage across the capacitor. And you can tell this because you know the equation Q equals CV. Now the capacitance of the capacitor is an intrinsic property of the capacitor that doesn't change. So you see here that you know, voltage and charge will change proportional to each other, proportional as a function of C being a proportionality constant. So with this equation, you can see, well, whatever pattern voltage follows is going to be the same pattern for charge Q. So that's what we see here. You can also conceptually think about this. You know, at first there's no charge on the capacitor, no Q. So, you know, it starts off with 0. I don't know why it does that. It starts off at 0. And then slowly, as current comes out of the battery, as charges come out of the battery, charge will slowly build up on the capacitor. And then as time goes to infinity, you get to a maximum amount of charge. So here is the equation for charge. It's obtained fairly easily. The voltage equation was voltage of the source times 1 minus e to the minus t over RC. And I told you that there's a relationship, or I reminded you that there was a relationship between charge and voltage, right? It's the capacitor equation. Maybe I'll say that. It's the capacitor equation. And so all you do here is you multiply this by C, you multiply this by C, and then you can get Q of the capacitor is going to equal to Q naught 1 minus e to the minus t over RC. So it's really the same equation as we saw before with voltage. There's really no difference there. Now the last thing, this is more of a property of mathematics than it is of physics. We see here that time is very obviously an important aspect to this equation. Like, of course, the end behavior is important as well, like what the maximal value is. You even learn these sorts of tricks in math class. What's the local max, absolute max? Like, these are just useful features of math to know. But the other thing is time. Time is also an important feature here, how long it takes to charge, how long it takes to discharge. And we see here that the time variable, negative t, is modulated or scaled by the variable R times C, resistance times capacitance. So we say that the time constant, tau, this is called, maybe I'll change it to red, this is called the, oh, I said red, okay, whatever. Time constant, tau, oh, I don't know why it's being wavy. Time constant tau, Greek letter tau. We use the same symbol for torque, unfortunately, is going to be equal to RC. Now, what does tau equal RC represent? You might recall over here, seeing these graphs, you see these little boxes here? Those boxes represent the value at the time constant. And why is it called time constant? Why is it equal to RC? This is what we call, and this is a very common term in mathematics. This refers to something called E-folding. And E-folding refers to a factor of e to the minus 1, or simply 1 divided by e. Now, when we say time constant, we say it's the time at which the value is 1 over e. So if you have the expression e to the minus t over RC, the time constant is going to be the value at which it's 1 over e. So we say, well, what time will e to the minus t over RC be equal to 1 over e? And the answer is simply when t is equal to RC. If you look at that equation there and you plug t is equal to RC, then you're going to get e to the minus RC divided by RC. That's e to the minus 1, which is exactly the definition of E-folding. Now, why E-folding? Why 1 over e? That's arbitrary. You know, why not 1 over e squared? You're not wrong. It's arbitrary. We want sort of a benchmark. We want a sort of a time frame that we can visualize in our heads to figure out over what time it has diminished by a certain amount, right? Whether that amount be 1 over e or 1 over e squared, it doesn't really matter. We just had to pick something. Now, why e? Well, because e is the base, right? So if it was a different base, it would be like 2-folding instead of e-folding. So anyway, before we move on, let's do an example. So consider a series RC circuit as shown below in the figure, where we're given the value of the resistor. It's 1, oh, maybe I'll change it to black so it doesn't blend in, 1 mega ohms. R equals, the capacitor here is going to be 5 microfarads, and the battery here is 30 volts. Find part A says, find the time constant for the circuit. Okay, well, the time constant is R times C. R is going to be 1 mega ohms. Mega is times 10 to the 6. And capacitance is 5 times 10 to the minus 6, because micro is times 10 to the minus 6. So overall, this is going to be 5. And the units, if you look at the units, it has to be seconds. And if you are confused why the units have to be seconds, look at the equation, right? The exponent here has to be unitless overall. So how do you get a dimensionless quantity? The numerator and the denominator have to have the same units. So the numerator is t in seconds, or minutes, or years, or weeks, or whatever, unit of time. So the denominator mathematically also must be a unit of time. So seconds. So that's part A. Part B. Find the maximum charge on the capacitor after the switch is thrown closed. So here, they're not really asking us about kind of what happens in the middle. They're asking us what happens at the end. You know, yes, this question is acknowledging it will take some time to charge. Yes, it's initially uncharged. After you close the switch, what will the maximum charge be on the capacitor once it's fully charged? So to answer part B, we first recall that when it is fully charged, it will have the same voltage as the source. And I said that, where did I say that? Where was it? Here, I said that here. Okay, so if it has the same voltage as the source, then the only way to relate charge and voltage together, we use the equation Q equals CV. And we know the capacitance. The capacitance was what, 5 microfarads. And V changes with time, but specifically we want to know when it's fully charged. So it's a very specific V, and we recall from the lesson that the specific voltage when it's fully charged will be that of the source, and the source voltage was 30. So this is going to be 150 times 10 to the minus 6 coulombs, which is 150 microcoulombs. Okay, so that's how you do B. And then C, oh, I'm writing C in red. C, find the current in the resistor 10 seconds after the switch is closed. So we look at the current equation. Where's the current equation? There, the current coming out of the source is going to be voltage source divided by the net resistance. So the current coming out of the source is going to be the voltage of the source divided by the equivalent resistance of the circuit. In this case, it's simply just R, times, what did it say? Times e to the minus RT, e to the minus R, oops, not RT, sorry, e to the minus T over RC. And we have all of this. What do they want? 10 seconds? 10 seconds. Okay, so this is going to equal voltage of the source divided by the net resistance. The net resistance is simply 1 times 10 to the 6. E to the minus 10 seconds over RC, which was 5. Right? RC was the time constant we know is 5. So this is going to be 30 over 10 to the 6 times e to the minus 2. So this is going to be 30 times 10 to the minus 6 over e squared. That's current. So this is going to be 30 over e squared microamps. 10 to the minus 6 is micro, so microamps. Now E is around 2.7. I don't have a calculator with me, so I'm going to say 2.7 is pretty close to 3. 3 squared is 9. I know 2.7 isn't 3, so maybe 9 is going to become like 8 or something like that. So 30 divided by 8, something around there. So without a calculator, I can ballpark this to be, you know, around 3.5, maybe around 4 microamps. Somewhere less than 4, obviously, because 8 times 4 is above it's above 32. So I know it's less than that. So somewhere between 3.5 and 4. Again, without a calculator. So if you had a calculator, you could calculate it more precisely. Okay, now I just wanted to show you some uses of a capacitor. One of which was a defibrillator for sure. A defibrillator is kind of interesting. A defibrillator, the schematic for a defibrillator is going to look something like this. So there is a switch here, and when this switch is closed, when this switch is closed, you are charging the capacitor. You know, it's like you see all those doctor shows where they say like charging, right? This is what's happening. They're connecting the circuit. Now I suppose technically there'd be a resistor somewhere in here as well. Otherwise you'd burn out the capacitor. But point being, one half of the circuit charges the capacitor, and then you charge the capacitor full of charge. And then what you do is you change the circuit, you switch the switch to the other side, and then the battery is no longer, I mean, the battery's still around, but it's not electrically connected anymore because you've broken that half of the circuit. And then when you say clear, you know, you push the buttons on the paddles, you know, that's you closing the other switch. And then what that does is, I didn't mention what this was. This is called an inductor. We're going to talk about that later in this course. So for now, just go with the flow, no pun intended. And what you're doing is you're discharging the charge on the capacitor through the human or through the patient. And, you know, that's pretty much how a defibrillator works. Now, you might be thinking to yourself, well, Mark, why don't you just, you know, if the maximum voltage on a capacitor is that of the battery, why use a capacitor at all? Why don't you just use the battery to shock the person? I don't know if you've ever done this, but if you've ever put a 9-volt battery on your tongue, you'll feel your tongue feel numb and weird, you know, because you're getting a little bit of an electric shock. So why not just use a battery, and why use a capacitor at all? The answer is actually a physical limitation of a battery. The energy that is stored in a battery is chemical in nature, right? The way a battery works is through a series of chemical reactions. In order to shock a human's heart, right, the purpose of the defibrillator, you need a very rapid current over a very short amount of time. And a chemical battery is not able to deliver that much charge and current in such a short amount of time. It's limited by the speed of the chemical reactions. And you might remember from chemistry, there's a speed to every reaction. So a capacitor is not limited by speed of chemical reactions. There's just an immense amount of charge on these plates, and if everything is a conductor like copper wires and metal plates, there's hardly anything there to impede the flow of charge, well, other than the resistance in the human body. So they use a capacitor to get around the fact that the battery can't keep up with the amount of current needed for the job. So that's a defibrillator. There's a quick video here I want to show you. It has nothing to do with a defibrillator, but it's somebody who has opened up their electric amp, you know, from their guitar or something like that, and they're measuring the voltage across capacitors when the amp is on and not on. And you can see here on the display, kind of what happens to the voltage when he turns it on. You can see how it builds up slowly. You can see on the display how when he turns it off, you know, the voltage doesn't just immediately go to 0. It kind of dims down over time to sort of show you graphically, or to show you in real life, kind of the graph that we just looked at is real. So I hope you can enjoy this video, and it's only a couple minutes long.
The purpose of this video is to dispel some myths about discharging a tube amplifier. I'm using a Fender Blues Junior here as an example, but it applies to any other tube amplifier. And as you can see, I've got a voltmeter hooked up to the main power supply filter capacitor, and it's measuring 4 volts right now, which is just a kind of a chemical residue in the electrolytic capacitor. It doesn't really mean anything. It's just a byproduct, not at all important. I'm going to turn the amplifier on and then turn it off quickly. And now you see that it's going down. It went up to about 330 volts, and it's slowly going down, 266, 265, and it's discharging slowly, just leaking through various components inside the amp and natural leak down that you get with electrolytic capacitors. But that's more than enough voltage to knock you on your tail, so you don't want to mess around with that. Now, one way to discharge a cold amplifier like this is with a simple jumper wire with a 10,000 ohm resistor, 10K resistor held in one clip. Now if I touch that, actually anywhere around here, it'll take the voltage down rather quickly. 84, 60, 22, 16, 18, 12. Anywhere in the power supply will take it down. Now we're down to 1 volt. Okay, so that's a very safe and easy way to discharge any amplifier. The 10K resistor only prevents sparking. I could touch it directly, but I would get an arc. The 10K resistor slows down the discharge and makes it easy. Now let's do the same thing again. We'll bring the amp up to full operating voltage, which is, in this case, we see 347 volts, 348. And as the tubes warm up, you'll see that the amp will actually drop in voltage because the tubes will start conducting. Now it's down to 333, 34, 330. So this is kind of a normal voltage that you would see in a Blues Junior with normal operating conditions. And now you can play through the amp. It's live. And now, if we just turn it off, remember we turned it off before when the amp was cold and nothing happened. Now I'm going to turn it off and watch how quickly the voltage goes down. 50, 42, 26, 16, faster than it did through the 10K resistor. 3 volts, 2 volts. Why? Because it's conducting through the EL84s primarily, and the other tubes, but these guys are always using a lot of current all the time. So simply turning off a warm amplifier is all you have to do to discharge it. So now we can strum it, nothing is coming through the amp. And this is ice cold. I can touch it with confidence, know that I'm not going to get knocked on my tail or anything like that. So what about the old myth of having to strum the guitar while you're discharging? Let's take a look at that. We'll bring it back up to operating voltage again. So we're stable at around 334 volts. And we have a normal sound. And now we'll strum while we're discharging. Powerful E chord there. And you notice that it discharged in exactly the same way as it did when we didn't strum. There is no reason to actually strum the guitar. That's just one of those internet myths that gets perpetuated. The only thing that the strumming does is confirm that all of the current is gone from the tubes, but it can be deceptive. If you had turned the amplifier on and off quickly and these were cold tubes, it would hold a charge and it wouldn't play when you strummed it. So the safest thing to do is always to bring the amp up to full operating temperature so you can play through it and simply
Okay, so that was just a short little video. I know a lot of people, whether you're going to med school or forensic science, you might play an instrument that's, it's pretty common. Even if you don't play an instrument, you would have at least heard of or seen an amp before. So the whole premise of this video was, when you turn on an amp, and then you turn it off again, there's a myth that goes around that says you have to strum it to discharge the amp. And the myth is there because they say when you turn it off, you have all these capacitors that have built up charge, and when you turn it off, there's nowhere for the charge to go. It just sits on these capacitors. And what this guy was explaining is the tubes in an amplifier, and if you don't know what tubes in an amp are, that's okay. You don't necessarily have to know, but they're more old school. I don't think tube amplifiers really exist anymore anyway. They're more digital now, but tube TVs back in the 40s and 50s, tube TVs were like the first generation of TV. Tubes, when they were cold, didn't conduct. So if you turned on the amplifier and turned it off right away, the myth sort of started because if you turned it on and off very quickly, these capacitors would be charged, but the tubes would not be conductive because they weren't warm. So it wouldn't act as a resistor and it wouldn't discharge the capacitors. So the myth was you had to strum your guitar to sort of discharge the capacitors as another means to conduct electricity. However, this guy was saying that's sort of true. It's easier to just, when you turn it on, leave it on for 10 seconds for the tubes to warm up. And then when you shut it off, when the tubes are warm, they act as a conductor and they'll bleed the charge out of the capacitors naturally anyway without you having to do anything. So anyway, it's a nice little example, I guess, of how a physics idea has sort of pervaded into a common myth. They said the same thing about TVs in the 50s and maybe even the 60s when they were tube TVs. They always said, the tubes were made of glass. They said, if you never turn on a cold TV, you'll crack the tube, right? Because it would warm up so rapidly, the glass would expand and then crack. They said make sure the tubes are warm, room temperature, 20 degrees Celsius, and then turn on the TV so that the glass won't crack as they warm up when they're conducting. So I don't know, nice little tidbit of information there. So that's it for RC circuits, and that's it for electrodynamics. So I'm going to end the video now to separate it from magnetism, and I'm going to resume another recording with magnetism. Okay, ciao for now, guys.